So I'll be talking about stability of spiral nebulae and the origins of modern cosmology. This is a talk that's focused a lot of my research for the early 20th century, but in keeping with the thrust of the meeting, I will make forays into the latter half of the 20th century as need be. So I'm actually going to start off not even in the 19th century, but in the 17th century with the equilibrium figures, and I'll talk about those from Newton to Poincare, just do some scene setting, then talk about spiral nebulae as a research object in the first years of the 20th century, move into kinetic gas theory in the hands of Lord Kelvin and Poincare, then focus on dynamic models of the universe from 1911 to 1932, and then finish up with Lin-Shu theory, which is the 1960s. All right, so this is a story about echoes of mathematical physics throughout the ages. Let's start off then with equilibrium figures of stability. And the question that a lot of people asked back in the 16th and 17th century, why does the rotating Earth not fall apart? Newton's answer to this was, of course, that it's held together by the force of gravitation. And Newton argued that for a homogeneous figure of a radius r rotating with a speed omega, its ellipticity is related to the centripetal acceleration at the equator divided by the mean gravitational acceleration at the surface, such that you get this nice relation between omega squared, r squared, and gm. Consequently, Newton found famously that the Earth's figure of equilibrium is an oblate spheroid. Now, this was a shocking thing to come up with, and particularly for the Cartesians. And so finally, there were a number of these Cartesians who were in the Paris Academy of Science. They finally figured that they could do away with Newton once and for good if they just measured the actual ellipticity of the Earth, and lo and behold, Newton was right, and that was about in the 1730s, and so that kind of established Newtonian physics, even in the heartbed of the Cartesian world of Paris, and from then on, Newton's physics had the droit de cité, as we'd say in France. Of course, there was a lot more work that was going to be done mathematically on these figures of equilibrium, Maclaurin, and then in the 19th century, Jacobi, who showed in 1834 that ellipsoids of 3 unequal axes can also be figures of equilibrium. Also in the 19th century, mid-19th century, another question that interested a lot of people ever since they were discovered was, what are those rings around Saturn made of? Are they solid? Are they fluid? Maxwell posed this question and worked it out dynamically and showed that if they were solid or fluid, they would break up. So much for that hypothesis. What does that leave? Well, that leaves gas or particles. And so he plumped for particles, modeled the rings of Saturn as particles, each oscillating radially around the center point. And then that seemed to work fairly well. And not only that, well after Maxwell's death, but before the end of the 19th century, Keeler, who was in Allegheny Observatory, confirmed Maxwell's conclusion spectroscopically. So that was a good point for Maxwell's theory. His model inspired Poincare in the 1880s and Lindblad in the late 1950s. So we'll get back to that. But let's turn directly to Poincare's work of the 1880s. He took up this problem of stability then with using some new methods and introduced, in line with these new methods, a new figure of equilibrium, which is known as the pair. In French, this is a figure périforme, so it's pair-formed. And so the interesting thing about this particular figure was that it could evolve, and naturally, through cooling, it could provoke division. So you'd have one figure of equilibrium that would become 2 figures. And this process, he suggested, was the origin of celestial objects, for example, binary stars and probably other things in the universe. And here we have a picture of this this Pear figure. You can see it's a little bit narrower here. Doesn't look too much like a pear, but it is narrower. And the idea is that if that gets narrower and narrower, eventually you're going to have two separate parts of this object. So this excited a lot of people, astronomers and theorists. One of the theorists who was particularly excited by Poincare's work was Lord Kelvin. Lord Kelvin had his own research problems that were interesting him. Notably, in the 60s, he was worried about how temperature varies with the Earth's atmosphere as you change altitude. This is a topic that had interested a number of mathematicians, Lane, Ritter, and Emden among them. Thompson was particularly interested in estimating the age of the sun so he could compare it to the case of Darwinian evolution. And famously, of course, he came up with the age of the sun, which was much less than that needed for Darwinian evolution. This problem, Thompson kept coming back to it over the years since 1862, and at the end of his life, could be the last paper that he ever published, was entitled On Homer Lane's Problem of a Spherical Gaseous Nebula. So these are problems that he was very much engaged with, and it's kind of a signal of the times. I'd like to go back to an earlier paper of Kelvin's, because it kind of launches the whole scheme of new models, star gas models of the universe and of other objects like globular clusters and eventually spiral nebulae. So in 1901, Thompson decided to model the universe as a sphere of radius r centered roughly on the sun with a homogeneous matter distribution. This is a pretty typical model. If astronomers did believe that the sun was located reasonably close to the center, if it wasn't at the center itself. His model neglected non-luminous matter absorption and non-gravitational forces. He made the pretty plausible assumption that stars have no velocity at the edge of the sphere, and then just a normal Newtonian equation of motion. He determined mass density of his universe by just spreading the solar mass out to a volume to the nearest nearest neighboring star, and that would then, he figured that the sun is typical, and so that would give him the average mass density for this homogeneous sphere. And then from energy conservation and looking at the velocity of stars near the sun, which is supposed to be near the center, he could determine the radius of the universe. Pretty tricky. And so he came up with the figure that he came up with using a known velocity of stars near the solar system was 10,000 light years, which happened to be what astronomers then believed to be the dimensions of the known universe. Currently, it's a bit larger, it's about 85 to 100,000 light years, not including the dark matter halo. You could also then determine the number of the stellar population in the universe. He found it to be 1 billion, which was higher than current estimates, and a bit lower than today's estimates. So I think this is interesting, and he's got reasonable, these are back to the envelope calculations that give him reasonable results given the level of the precision of his data. Anyways, and what I want to suggest is that this simple calculation inspired other theorists and helped launch cosmology in the early 20th century, well before Einstein comes around. There are, of course, sticking points for Thompson's model, which are that he assumes a spherical universe in adiabatic equilibrium. In 1910, these assumptions were not filled because it was known that the Milky Way is not spherical, and there were also currents of stars or star streams, which suggests it was not an adiabatic equilibrium. So these were difficulties for Thomson's models already then. However, both these objections would be allayed later on in the century, as you know. Let me move now to the case of nebulae. What was the position of nebulae at the early 20th century? Well, James Keeler, was director of the Lick Observatory at the end of the 19th century. He was also the co-founder of the Astrophysical Journal. In 1899, at the Lick with a 36-inch Crossley reflector, Keeler was able to make photographic plates of several spiral nebulae, including M31. The images that he obtained were pretty amazing. They were finest ever obtained, and they gave a great deal of detail that had never been captured before. And the cool thing about photography is he could circulate these among other astronomers and also publish them in popular scientific press. So these made quite a splash. Keeler claimed that from these images that most nebulae are in fact spirals. And he estimated from his plates that the number of spirals visible with the Crossley was around 120,000. That's a lot of spirals. This then made a splash, as Hoskin observed in '82. He said the upshot of this this photographic exploit of Keeler's was that a fascinating new field of study was born, which is to say the study of spirals. He's brought this to the attention of astronomers. Now, he wasn't alone. Of course, Stratanov, who was director of the Tashkent Observatory at about the same time, made a count of nebulae and came up with 9,943. So we're a long way from 120,000. But these are known and observed nebulae up to 1900. He also compared the distribution of the nebulae with the distribution of stars and noted that most of your nebulae are found where there are few stars. So there's some kind of complementarity here. We have reason to believe, yeah, that was probably right and still right today, but for different reasons, of course. Nonetheless, that the question of the distribution of nebulae is clearly posed by Stratanov. Another fellow, Cornelius Easton, drew his models of, so these are drawings of the structure of the Milky Way. One of these drawings by Easton, published around 1900, included a spiral. So now we've got clearly expressed the idea that Milky Way itself is a spiral. Easton noted Keeler's remark that spiral nebulae are normal celestial objects. This view of spirals would be then confirmed 25 years later by Hubble's classification of extragalactic nebulae, which also considered, as we know, spirals as a particular type of nebulae. So let me move on to our theorists now, James Jeans and Henri Poincare, and I've listed here some of their greatest hits, as it were. Jeans's study of the stability of aspherical nebula in 1902. This gave rise to the well-known objects such as the Jeans mass, Jeans length, Jeans instability, and the Jeans swindle, which I won't go into because I don't have time. He also published a textbook on the dynamical theory of gases. Poincare, for his part, published a paper on the Milky Way and gas theory in 1906. It was both in French and English, and published what is plausibly the first textbook on cosmology in 1911, his Lessons on Cosmogonical Hypotheses. So this is what Poincare, his take on the on nebulae was in the early years of the 20th century. Spiral nebulae had been noted then to have a continuous spectrum Although it was a failure to resolve individual stars implied for him that there are other Milky Ways at immense distances. He was required to discount Boland's measurement, his singular measurement of M31 parallax as 0.171 seconds as unreliable. As it turned out, yes, it was unreliable. It was wildly unreliable, but he had somehow the good guiding star to tell him that that was obviously wrong. He also saw the Milky Way as a spiral galaxy with the rotation period determined by its density of 500 million years. Slipher and Wolf, after his death in Poincare died in 1912, but Slipher and Wolf later observed inclined lines from M31 and other galaxies suggesting a rotation. Actual estimates of the Milky Way rotation put it at between 220 and 360 million years. So again, he's off by several hundred million years, but given his model, it was maybe not too bad. All right, so that meant I only have 5 minutes left, huh? I'll move this. I'll skip a bit. Poincare also remarked at that time that well, here I've got a quote from him. You can read it. He said, we'll be able to know more about proper motions of stars in 100 years when we'll publish the second edition of the Carte du Ciel. As you know, this Carte du Ciel, they were involved in mapping and the position of stars. And so the way you determine proper motion is by letting time pass and comparing photos. Well, that's one way to do it. And so, in fact, that's what people did. So here's my foray into the second half of the 20th century. Well, first we go back to the 1054 when a guest star was observed by Chinese, Japanese, Indian, and Arabic astronomers, later identified as supernova 1054. We're going to hear more about supernovae from Adele in a few moments, I suppose. In 1913, Slipher showed a doubling of lines in the Crab nebulae with his high dispersion spectrograph, noting and observing that it was expanding at 1,000 kilometers per second. Less than a decade later, Knut Lundmark noted that this Chinese guest star was co-located in the Crab nebulae. So now you've got things coming together. As we heard from Vanda earlier, the Crab nebulae was in the 1950s was assimilated to a betatron for the synchrotron radiation. But what I want to get us back to Keeler was, so there was a pulsar discovered in the Crab nebulae with antennae at Green Bank and Arecibo, and it was found out the next year that it also emitted optical and X-ray pulses. Okay, I'm down to my last 2 minutes here, and later gamma rays. Now, the determination to the Crab Nebula had been made by Virginia Trimble, who I saw is involved in this meeting in 1973 at 2 parsecs. Now we come to Keeler's part. So Keeler's been dead for now by 70 years. We're in 1969, 1977 actually. But Wyckoff and Murray compared Keeler's 1899 photo of the Crab Nebula taken then with the Crossley, and compared we're able to find this pulsar on the photo, and then measure its proper motion. This provided, as he said, conclusive kinematic evidence linking the filaments of the nebula and the pulsar. Here I've got the marked up photo from Keeler. If you look closely in the middle, you can see one of these points is labeled with a P. These are reference stars, the other numbered points. So here you've got, so that Keeler had an echo much later on. But I see don't have much time to continue on with this, so I'll head directly into well, when I get to have time for the reinterpretation of data models, yes. So these, and the story of the 1920s was that, yes, these the model of the universe based on these star gas theories ended up with where was I want to see it? Yeah, the Kapteyn universe. The Kapteyn universe. So both Jeans and Kapteyn published models. Kapteyn came up with a model for the universe based on this Schwarzschild velocity ellipsoid. 1922. This was now a rotating flattened ellipsoid. Right, so this is not a. So this could be a sort of figure of equilibrium. However, Kapteyn recognized that the model was not realistic. It did not correspond to what was known of the Milky Way. However, this model would be reinterpreted, particularly by Oort in 1932, who was able to salvage this 1922 model and determine the potential well across the galactic plane with new data. So there was, once again, old theories get chucked in the bin, and new theories emerge from them. And leading us to the last one. Do I have a minute here?
Yeah, please make your conclusion. So
okay, fine. All right. So this is just concluding. So this brings us after 1932 is as a bit of a low point there, but in the 1960s. C.C. Lin, who was a former student of von Karman and who had improved Heisenberg's theory of turbulence, he was a professor of applied mathematics at MIT. Shu was who wrote his senior thesis at MIT under Lin's guidance. And so Lin had felt that there was the apparent stability of spirals hid their true nature, and that the great distance of spirals hides motion inside the arms of the spiral. And so what we observe is a quasi-static wave pattern, not a fixed distribution of matter. So this is the occasion for him to introduce what's called the density waves, which actually has its origins in Maxwell's solution for the rings of Saturn. So here we have a long-term echo with Maxwell's model. Now you wonder, okay, well, what happened with the velocity profiles at the time? This is more or less simultaneous with the first velocity profiles, which were published in the 1960s, showing surprisingly flat curves and then later motivating a search for dark matter. So nonetheless, I think Vera Rubin herself had said that before she died, said that it was not yet clear whether the observed curves were consistent with changes in the gravitational potential in the spirals themselves. So that's still a research question. So that's pretty much where I wanted to finish. So we have these models of the universe that founded in the 20s due to improved data and distance in the spiral nebulae. However, the Kapteyn universe of 22 was salvaged in 32. I didn't get to talk about the Chandrasekhar's stuff, but the Lin and Shu then revitalized this theory with the field with their theory, which, however, remained problematic from a theoretical standpoint. Thank you. That's all I have time for. Yes.
Thank you very much, Scott, for this very dense talk. There are not many minutes for the question. We have 5 minutes, so I think a couple of questions. There is a question by Luisa Bonolis, which I will read. Both Heisenberg and von Weizsäcker were interested in turbulence problems. How would you place von Weizsäcker's model with interplay between turbulence and rotation's role in a protoplanetary nebula in which long-lived vortices can capture a large amount of solid particles and initiate the formation of planets? Probably if you read the question, it's clearer.
Yes, that's a great question, Luisa. Thank you. Unfortunately, I'm not familiar with von Weizsäcker's model. I know a little bit more about the Heisenberg theory, and of course, there is an interesting element that plays into the Lin-Shu theory via Bertil Lindblad's very long scale work that goes from late 20s up to the early 1960s, right? So he struggled with this problem for a long time, trying to understand the structure of spirals, and actually using ideas that were then captured in a certain way by Lin and Shu, and may have some interplay then with von Weizsäcker's model. I have to look at that. So, but thank you for the question. That could be an interesting point for understanding what's happening in the 1960s as well.
Thank you very much. There is a question by Adele, and I think that this is the last one. The next questions have to be written in the chat. Thanks.
Okay, thank you, Scott, for your very interesting talk. It's all very quite new for me, many things. So I ask a naive question about, can you extend about what you were telling about Pear Rubin? The fact that gravitational potential in spirals can be different and can from what we expect, and what's the position today? I am curious.
Okay, yeah, I couldn't tell you what. Thanks for the question. I couldn't tell you what today's researchers say about this. What I did look at was Vera Rubin's review of observational studies of spiral nebulae, and she did take up this question, which is posed by the Lin-Shu model, right? Because the Lin-Shu model is unusual in that it has these gravity waves, which are then changes in potential. And there's that was part of the problem of actually working out the Lin-Shu theory, which, as I say, it still remains problematic, is seeing how the gravitational potential is actually plays out in the spiral itself, right? So this is we don't have the same just a flat gravitational potential. We know this is true for the Milky Way, right? This is what's driving a lot of the studies of halo stars to get a handle on variations of gravitational potential in the Milky Way. So what I understood Vera Rubin's question to be was, well, yeah, okay, can we explain the flat velocity profile via some kind of change in the gravitational potential across the surface of the spiral galaxy? Does that answer your question?
Yeah, and yes, thank you, Scott.
Thanks a lot, Scott. I think that we have to go ahead now. There's